This is Saxon Advanced Math, Lesson 82, and we're going to be talking about logarithms. We're getting a little bit further into our logarithm discussion. The first part, 82A, is taking the logarithm of, and we already understand this principle. We just need to apply it to logarithms. If I said it's just an operation, taking the root of 100 is raising the 100 to the 1/2, or taking the root of 100, there you go. This is the same thing with logarithms. If I say take the log of 100, I write it as log 100. If I say take the ln of 100, or the natural logarithm of 100, I write it as ln 100. Now, with that little bit of information, sometimes it's useful to work with exponential equations, and we're going to take the logarithm of both sides. Now, keep in mind, we have to remember what powers are first. 5 raised to the power of 2.3, 3y raised to the power of 4, and so on. Now, when I get to logarithms, the logarithm 1/2 x equals 2, you remember we can change this from logarithmic to exponential form. And when I do so, then I look at the base 1/2, and that becomes the base over here. The 2 is the exponent, and the x is going to be equal to on the other side. So everything has its place and it swaps, and when I work this out, I end up with x is going to equal to 1/4, right? Because this works out as 1/2 times 1/2, which is x, and that's 1/4. I do the same thing, remembering that logarithms have a base and an exponential that can be flipped around with using coefficients. So now this is not new, but we've been doing it the other way around, where we start with a coefficient and we make it an exponent. We can do the opposite of that as well. For instance, log 10 to the x could be rewritten as this x is an exponent. It could be a coefficient of just as well, x 10 log. Or if I had ln of 4 to the x, I could say that is the same as x ln 4. This allows me to solve for real world problems or actual problems instead of just changing the format up. Let's look at our first example, 82.2 or .1 here. And they ask for us to solve 10 raised to the negative 2x plus 2 equals 8. The first thing we're going to do is we realize that I could take this number and move it out here, right, as a coefficient. Well, let me take the log of both sides first. I apologize. If I took the log of this side and the log of this side, I end up with log 10 to the negative 2x plus 2 and log 8. Because I'm doing the same operation to both sides, I'm taking the logarithm of, I can do that. Then this becomes a coefficient. I was getting ahead of myself there. This can become a coefficient as negative 2x plus 2 out here times log 10 equals log 8. Well, what's the understood value when they don't tell us this? Just like there's an understood 2 right here, there's an understood 10 down here. Log 10 is 1, and that gives me 2x minus 2 on this side. On this side, I use my calculator, and I find the log of 8, and I get 0.9031. Now I just solve this like a regular algebraic problem because I no longer have the exponentials that were very difficult. This is a lot quicker than other methods of doing this and allows me to solve for real problems, right? Taking the log of both sides. Now, what if that was ln? And this 82.2 is very similar, except it's dealing with ln. Solve e raised to the negative 2x plus 3 equals 5. What's the opposite operation of the e, which is ln? So I take the ln of both sides, the natural logarithm, and when I do so, I realize that this negative 2x plus 3 can become a coefficient. And then I take the ln of 5 and get 1.60494, and I ln base e cancels out, and then do negative 2x plus 3, and then I solve it algebraically. Now, let's get into a little more excitement here. 82.3 starts to be where this is an actual issue, right? 5 to the 2x minus 1 and equals 6 to the x minus 2. We could solve this without using logarithms, but what a pain it would be, because I would have all these variables in my exponents and have variables on both sides of the equation. But if I just start with taking the logarithm of both sides, I can say the log of 5 equals the log of 6 with these same exponents. These exponents, though, remember, can become coefficients, so if I move them out to the front, I'm left with this. Now I have something that goes in my calculator, log 5 and log 6. When I do so, I get 0.6690 and 0.7782. I go ahead and distribute those, And once again, we get back down to a regular algebra problem. X is negative 1.3833. Now, this is a lot easier to do using logarithms than normal algebra, and that's why we're doing it. Look at 82.4, and it's the last one we'll do very quickly here. I've got 4 equals 6 e to the 2x plus 3, and this is going to use a little bit of both terminologies that we've had with logarithms, because I'm going to be able to immediately take the ln of both sides, right? So I know at ln 4, I can hit that on my calculator, but I take the ln of this side, and this I can't put in the calculator. But keep in mind, multiplication of bases is addition with logarithms, or ln, or natural logarithms. So I separate this into a ln 6 and ln e raised to the 2x plus 3. By doing so, I know what the ln of 4 is, right? I know what the ln of 6 is just by using the calculator. I know what the ln of e is. Well, in this case, it cancels out and leaves me with 2x plus 3. So when I put all these together, I end up being able to say 1.3863 equals 1.7, this is the ln of 6, 1.7918, and then I also notice I have that 2x plus 3 that became a coefficient, so it's just 2x plus 3. Now I'm going to do some algebra, right? Take away 1.7918 from both sides. I take away 3 from both sides. I divide everything by 2. Once it's all combined, I get x is negative 1.7028. These are not terribly difficult if you're looking for patterns. How could I cancel out things? I don't like having variables and exponents. Let's get rid of them. I take the log of both sides to do so because I know that it's going to cancel some things out. It also allows me to move things to the outside. Exponents become coefficients, or coefficients can be exponents. Remembering my other rules. Division is subtraction of bases, right? And addition is multiplication. So I have to keep those in mind because I will be using those throughout these type of problems on working with logarithms in a little more advanced way.